3, 2, 1. All right, we're in CCR world again. And, of course, we have a new face now, Jeffrey Richter. Who are you? Why are you here today?
Okay, so first, I'm Jeffrey Richter. I'm one of the partners of a company called Wintellect. We do training and consulting, debugging services. I also teach a course on threading. So that's
the connection.
That's what the company is. I also write the Concurrent Affairs column in MSDN Magazine.
All right.
The most recent issue, well, actually, it's coming out very shortly. The next issue will have our column by me on the CCR inside of it, and we have a website that we'll give you at the end where people can go and get that article on July 24th. Yep. Right? It's going to be live on the website.
Okay.
Okay, so that's me. Now, how I got involved in the project.
Yeah, exactly.
Is that well, I've been doing a lot of threading stuff for many, many years. In my Win32 books, I had many chapters on it, so I kind of have a reputation and a lot of experience with threading, and I just know people at Microsoft. So I got asked around the beginning of the year, or the end of 2005, if I would take a look at the CCR and maybe help out with the object model, because I'd also done a lot of work on the Common Language Runtime team for 6 years with frameworks and building APIs and things like that. So it just seemed like a really good fit. And then George and I, we just get along great.
Excellent. And of course, George is one of the masterminds behind the CCR. And do you want to introduce yourself again? I mean, you've been on, this is going to be the third time you've been on Channel 9, but let's do it again.
I feel sick and tired of seeing me, but so I'm George Chrysanthakopoulos. I've been at Microsoft for 10 years. I started working on the CCR because we were doing so much, again, asynchronous I/O. It was never about concurrency, again. It was just about coordinating a lot of I/O. That we wanted something in managed code, and as you saw in the robotics video, we're now applying it in a domain that I think is very appropriate. A lot of loosely coupled components.
Absolutely.
So again, I mean, Jeff, actually the way we found about Jeff is because he had published an article about a reader-writer lock that was basically using a queuing mechanism and delegates. And, you know, my manager at the time, George Moore, he said, hey, that's really similar to what you're doing with interleave, which is one of the primitives in the CCR. It's just a general version of what Jeff had done. So we basically started exchanging email, and then we did a pitch to him, and I explained how it worked, and I think he bought into it. And then he decided to, you know, work with us to basically make it more approachable. Because I was doing a lot of nifty... I still like them more. A lot of nifty tricks with operator overloads, and he has a lot of experience, as he said, with a common feel that the C# libraries and the .NET libraries should have. And then we started working on that, and I think it went really well. And that's exactly what we shipped. We shipped basically the object model that became...
And that's in the robotics SDK.
This is in the robotics SDK.
Today.
People can download it, just use the CCR by itself and all that.
Cool. Now today we're going to focus on some of the work that you guys have done in your demos with...
Today we're going to look concretely at the CCR. We'll look at some C# code. So it's going to be kind of in two parts. The first part is I'm going to walk through just some of the technology. What are the classes and things like that to kind of show architecturally how the CCR exists internally.
Okay.
And then after we get some of that underneath our belt, then I'm going to start showing how it can be used to do asynchronous programming to be real. So the first couple of demos are really just to get people familiar with the architecture.
Okay.
And then we're going to move to why you would want to really use this.
Absolutely.
Okay.
Well, let's dig into it then.
Then let's do it.
So I'm going to come over here, and I'm going to zoom into this guy, this nifty new camera.
Okay, the code that we're looking at is the sample code that I wrote for the MSDN Magazine article that's coming out later this month. But now you'll see it live. And then, of course, you can read the article for a little bit more details. And there's some architectural drawings in that article, which I won't show here as well. So to use the CCR, it's really easy. It's really just in one dynamic link library. So I've referenced that in my Visual Studio project here. And then the classes are in this namespace, Microsoft.ccr.core. There's another namespace, this one, .arbiters at the end, which is for more advanced things, which we're not going to get into in this talk. So now, inside main, the first thing I'm doing here is I'm newing up a dispatcher. A dispatcher is like a thread pool. And the CCR has its own thread pooling mechanism, which you could use instead of the one that's inside the Common Language Runtime. But there's also the option to use the one that's inside the Common Language Runtime and use their threads rather than creating this separate thread pool. But this shows how to create your own dedicated thread pool for your own tasks. So I'm just newing up a dispatcher object. This 0 here there is the number of threads I want in the pool. If you set it to 0, it'll be equal to the number of CPUs in the machine with a minimum of 2, right, George?
Yep.
Okay.
And each of the threads, you can give them a name here, which is really useful in debugging too. In the Visual Studio, you can look at the threads window, and then you can see the names of the threads that are part of this particular thread pool.
Cool.
It'd be nice if the CLR thread pool did that, but it doesn't. All right, so that just newed up a thread pool there. Then, we should have turned your mail off.
I didn't catch that.
All right, excellent. Then here I'm newing up a dispatcher queue. A dispatcher queue is a queue, just like the CLR's thread pool has a queue where you can queue items into it. You can create a queue that connects up to this thread pool. One of the nice things about the CCR is that you can actually have multiple queues that are connected to the one thread pool, and that allows you to do priority queues or say that these things are more important than these other things, even though they got entered into the queue at a later time frame. Mm-hmm. So I'm just creating one queue here, and you can see I pass in, for this last parameter, the dispatcher that we're going to connect it up to.
That you knew just above it.
Yes, that I knew up just above it. And again, you could create multiple dispatcher queues and pass in the same dispatcher object there.
Now, why would you want to do that?
Again, for priorities, if you have certain events that are just coming in very quickly, but then maybe there's this other event that you want to give a higher priority to, rather than wait for all the other ones to come out, you could maybe look at this one. Do you want to add more to that, George?
Yeah, actually, another very common use, especially in robotics, is in queuing systems, you get traditionally, think of, so in the CLR thread pool, you see this a lot. Let's say you have, in the same process, you have someone emitting a lot of work items.
Okay.
Because they're very busy. And then you have some other, class or little process that emits an item once a second. Now, what will happen is if you have one queue, you will get a million items in front of you. And then you get your item, your 1 second item, sandwiched in between. Now, in OSs, underlying in the kernel, the way we get around that is we round robin between multiple queues. So a well-designed, concurrent system doesn't give you one queue to schedule work items for execution. It gives you multiple queues, even if they're all at the same priority level. What it allows you to do is you have one queue that's only one deep, it only has one item, but I will visit it every time. I will only pick one item out of this huge queue and then go back to the other queue. This way we ping pong.
Cool.
This keeps the system extremely responsive. Where, as I said, in the CLR thread pool, you can get blocked behind a sea of other items where you should be fair, and the round robin is one of the fair scheduling algorithms. And from the very beginning, and there was actually, a lot of people didn't buy into this, but from the very beginning you had to think of a fair scheduling. Otherwise you would get into a lot of problems people solved 30 years ago.
Excellent. Perfect.
Okay, so now we've created our thread pool, and we have created a single queue that we've attached to that thread pool. So now, again, going into the architecture, here's our first demo. In our first demo, I just want to shove a task into the thread pool and have it do some work. So I have this method called spawn demo, because I'm going to spawn a task, and I pass into it the dispatcher queue, the queue that I'm going to queue up this entry for. And inside here, I call arbiter.activate. Arbiter is kind of our one-stop shopping for all your arbiter needs. We just did that. And we'll take a look at it, but it's basically a static class with a bunch of static methods on it that give you an easy way to throw things in, and we'll see more of it in detail.
Now, can we just quickly, because as you know, when you name a class intelligently, let's talk about the term arbiter for people who, let's talk about
that will make more sense as we go. So I think maybe it'd be better to postpone that a little bit. But it kind of goes back to, I'll say this much about it now, right? The CCR is concurrency and coordination, and a lot of it's about coordination. And the arbiter aspect is looking at items that are coming into these queues and deciding how to coordinate the dispatching of those items. Okay, that's kind of the origin of the name.
Cool.
It's an arbitration that happens for every message. Yeah.
Now they have someone at restaurants do similar things, right? When they get the orders in and you have them dishing out stuff to people, it's a different
kind of like that.
All right.
Actually, yeah, and in big web servers, you have arbiters. I mean, think of little processes that arbitrate and decide. We hard code them in. Here, CCR codifies some of that stuff, makes it.
Absolutely. Cool.
So right now, on the arbiter, we have this other method, the static method called fromHandler, and it's really just saying that when this event appears in the queue, I have this handler that I want to go and execute. And then I passed in, using an anonymous method here, a name of a delegate. This delegate's a very simple method that simply calls a helper function of mine called MSG for displaying a message to display a message on the console window. So really what I'm trying to say here with this line of code is go into the dispatcher queue and queue up an item. That item should call this delegate method back, and it should display a message in the console window that simply says handler, just to prove that we got there. And so this looks like more complex code than what you would do in the CLR, which is simply called thread pool queue user work item.
Mm-hmm.
But thread pool queue user work item is, of course, assuming a particular thread pool, and it's assuming a particular queue. And now we have those things exposed to us, so we have more control with the CCR.
Cool.
So that's why the code's a little more complicated, but it's logically the same thing.
Mm-hmm.
Okay, if we execute this, that just adds this entry into the queue. The dispatcher is going to take up its thread and go and call this method back. And then I have this method here called hit enter, which I'll walk through this first time. It just puts the main thread to sleep for a quarter of a second, just to give the other operation a chance to execute. And if I switch over to the console window, you'll see that we did get this handler displayed out here. Mm-hmm. And my message function also shows the ID of the thread, so we can see which was the thread ID that processed the result.
Okay.
Then this just says hit enter, and then there's a read line just to pause. So there we see the result again. I'll just hit enter, and then I put a blank line in there, and then I return back. So I'm going to call hit enter frequently, and now you've seen it the one time, so I won't walk through it anymore.
And just to interject here,
Go ahead.
it's kind of interesting. The CC actually has this issue where in Windows, you start your exe and inherently assumes that you're a single-threaded sequential application. And this makes perfect example, the fact that you had to hit enter there. You literally have to block. You really have to wait. Because you're assuming you do this, then you do this, then you do this, and when you're done, you can exit your exe. But things almost never work this way these days, so we have to go out of our way to keep the other processors busy and keep the exe from exiting. So it's kind of a weird model that the CCR kind of exposes that and says, okay, we have to have this shortcut to keep us from running. Otherwise, it would exit. I mean, the NT process would shut down even if the CCR is scheduling things across processors. We'll literally have to block and waste a thread.
For demonstration purposes.
For demonstration purposes.
Yeah, for demonstration purposes. But, I mean, one could imagine a future version of Windows or operating system that had a CCR as an application model inside it where you wouldn't have to block and you just had all these events queuing up and being dispatched and coming back. And, I mean, that's long distance
Well,
future.
I mean,
But
I would just interject that you could test this concept out by working with the Singularity folks who are writing an operating system you guys could play around with and maybe...
It's actually not a big deal. It's just, and for us, that never really has stopped us because one easy way to get around this is you make it a Windows, you don't make it a console app, you make it a Windows app, and then it kind of stays alive for longer.
Understood.
Because Windows, again, has a similar model. You have events and you have to be alive. So you can get around it. You don't need a new OS to get around that.
Sure.
But it just shows that the thinking has been shifting to more like a CO work items type approach, if it's workable, versus a traditional approach. Yeah.
all right. So next is a port arbiter demo. In this example here, I'll scroll it to the top of the screen. I'm newing up a port. Now, a port is one of the classes that's in the CCR namespace, and it represents a queue of a particular data type because generics are used here a lot. So here I'm creating a port that can put strings into this port. And then on that port, I'm posting into it string A. Okay, so I've created this queue, this port, and I'm putting a string into the port. Now, right now, this port's not connected to anything, so it's not going anywhere. So right now, it's just holding on to this string and not doing anything with it. Now, the next line of code is where we start doing the coordination part of this. What this arbiter receive says is that we want to create a delegate that's going to receive an item from a port. And the delegate's the last parameter here, this anonymous method that takes something of type string. and then it says handling string, and it displays the S, whatever the string happens to be that was in the port. So here's a method that's going to get called whenever a string shows up, and it'll be passed in the string so it can operate on that string. This first parameter, true, false, has to do with persistence, and we'll talk about that a little bit later on. But false means it's non-persistence, which means this method will only get called once. And if anything else appears in the port, it'll stay in the port and not be dispatched off to the method.
Now, but if I may ask, because I'm learning as
Sure.
we're going, just like the audience is, you use port and queue interchangeably, and you obviously did that on purpose. So,
Yeah.
but we haven't really defined what a port is yet. Are you gonna, like, I don't like that?
Well, a queue would be items that need to be dispatched right now.
Okay.
All right, and a port would be a place where you can queue things up, and you may decide to dispatch them a little bit later on. Do you want to elaborate more, George?
Yeah, so the port is a very, very simple construct, and it has to remain simple. But it's a little bit more than a queue, in that it's essentially two queues. The port has a queue for items, for messages. And then it has a second queue for methods that are interested in those messages. So we can just call it queue, because that would mess with the queue construct in the CLR.
Sure.
And the queue construct in the CLR just queues a list of items. Our port queues two things: methods interested in processing those items, and the items themselves. Furthermore, what the port does, again in very small code, it basically it implements a two-phase procedure that allows those interested methods to see a message and say, do you want it or you don't want it? And it's exactly that feature, this two-phase procedure, that allows us to build these very interesting arbiters that you'll see later on.
Okay.
So again, the port is a little bit more interesting. It has things that are interesting in receiving messages and doing processing work,
Then the messages.
and the messages themselves.
Excellent. Thank you.
This helped me when I was first getting acquainted with the CCR. I started thinking of messages. I mean, George uses the term message all the time, and I actually found that confusing to me. When you new up a thread object in the CLR, one of the parameters you can pass is, well, when you start a thread, you pass an argument to the start method, and that gets passed to the thread that's going to actually do the work. Or another example is when you call queues or work item, you can pass for the second parameter some piece of state, and that gets passed to the thread that actually does the work. That's similar to what a message is. It's the piece of information that you want operated on by another thread, and I found that to be helpful.
It's more like an
Fantastic.
argument.
Yeah, it's like an argument,
Right.
more so than a message.
Excellent.
It helped me. Okay, so then I call activate on this arbiter class here, and I say on this queue, this dispatcher queue, which is now a thread pool, I want to go and receive anything that might be in this string port and go and process it with this method over here. And when I hit F10, I've now done that activation, and then I got to suspend the main thread, so I have my hit enter method, which I'll just hit F10, and we see that some other thread, this time it was a thread with an ID of 13, had this method called, and it was passed in string A. Okay. Again, we're not doing anything like big deal just yet. We're moving in really baby steps right
Good.
now,
Inch by inch.
inch by inch. All right, now here I'm taking that same string port I had a moment ago, and I'm posting another string into it, which is called string B. So the question is, will string B be processed, yes or no? What do you think?
Good question.
All right, I'll save you the
drama.
the drama. It will not be processed, and the reason is because this receiver was non-persistent.
Ah.
Okay, so it only is going to get called once.
Okay.
right.
That's what that means.
That's what that
It would
means.
be nice if the CLR events allowed you to do something like that.
Well, let's maybe some of the CLR people are watching this. Now we just quickly to sidetrack like we like
Sure.
to do on Channel 9. Why do you think the CLR threading model mechanisms didn't follow this approach? I mean, you
Right.
guys did something new, right?
Well, look, it has to be driven by an application model, right? And I think the CLR did an admirable job, and it did fine for the first iteration, which is essentially what the thread pool is. They said, look, people have the need to just hijack a thread, and they shouldn't have to worry about creating that thread. And they have a little work item, so let them do it. But there wasn't really any, concrete application that really primarily everything was I/O, everything. Still, most code in the CLR today is just calling an object and calling a routine, and the routine executes in the context of the caller. Where in our environment, that was never the case. You just never knew where the caller was even going to be, and it's just going to wake up somewhere and do something. So we just have different requirements, and we evolved, and even our first version was kind of like, you know, you just did on demand what people wanted, like some primitives. The second version created an actual architecture that you could extend properly and all that. So it's just a learning, and you know, the CLR team has been very. Jeff actually had made presentations to them, and I think it went pretty well and all that.
And so they're looking at this, and there's a chance that something will happen with it.
Something like that.
And in the end, you guys built this thing on top of the CLR, right?
Exactly.
True.
They helped make it possible.
Exactly.
Yeah. And in fact, when we get to some demos later, we'll integrate in with some existing classes that are already in the CLR.
Cool.
And we'll see how that works well.
Grand. So basically what we're doing here is a sort of like a screencast, live screencast.
Yeah.
So we'll see how this turns out.
All right, so here's my hit enter, and you'll see that we do not see string B. Right, because the receiver was not persistent. Okay, now we go back to the code. So now what I'm doing here is I'm going and adding another receiver, this time true. So this one will be a persistent receiver that says anytime anything appears in the string port, go and call this method over here and pass it in. Now this persistent, well, it's the moment I do this, string B is already in there so it can get processed. So this is kind of a cool thing too about the CCR, is that you can post things into the port immediately, and you can attach a receiver to it later, and then they get processed. Or you can attach a receiver early on, and then you can post things into it. So the order doesn't matter, which is really adds a lot of flexibility.
Sure.
You can implement a lot of the frameworks that people are trying to implement on their own, like futures and stuff like that. There are special cases of this type of approach. You can implement, you know, asynchronous objects and futures just by what he just said.
Okay.
Just post your item right now that you have it. Some later time it gets activated and it gets processed. You don't have to worry about, oh, is it ready? Is there somebody waiting for it? Don't worry about it. You can never tell in a concurrent setting with the order of things. So this is very flexible to let the race conditions basically disappear in some ways from your code.
And I have demos that are coming up later where I think it'll be more obvious the value of being able to do these in different orders.
Well, right now, but just that alone.
Right now I'm still going through architecture, baby steps. Okay, so after I activate this receiver on the queue, then theoretically everything could now be processed, or the one string, the string B, could go and be processed. But what I do now is I have a for loop where I put 10 more strings into the queue. So now there's going to be 11 strings in there. There's string B plus string 0 through string 9. I'm just shoving them in. Now the dispatcher is going to have its own threads that wake up, is going to go and process those. I'm just going to put a breakpoint here after the hit enter and just run to there. And in the console window, we'll see that string B came out, and then these other threads woke up and they pulled out string 0 and string 5 and string 1, and George actually has a 4-processor computer here, so they're all being processed simultaneously.
They just did. They were threaded, processed across 4 processors, and there you go.
Yeah.
Even if it just printed the strings, kind of overkill.
Yeah, and of course the console is serialized. But other than that, the throughput here was phenomenal.
Well, actually, we have time. We'll show you parallel build. We did David Lee here in the group did MS Build, which is the new build infrastructure, is sequential, and a lot of us have 2 proc machines. So very quickly, he wrote a CCR that does all the dependencies, create hierarchical trees, uses our arbiters, and just shreds through the build concurrently.
Wow.
And the sequential build, 4 minutes. The concurrent build, 1 minute 30 seconds.
Nice.
So you get almost a 3x speed up with a lot of I/O, a lot of stuff.
Beautiful.
Just a real app you can show.
That's great. Now, let me just interject. We only have about 30 minutes left, 37 minutes. So
We're probably not going to show you
volume.
Yeah. So
Because we can keep this at sort of like level 400 if you want. But okay, andiamo.
Okay. All right, I'll move a little more briskly. Here's a multiple item demo. So again, demonstrating the coordination part of the CCR. Here, I'm activating on the queue a multiple item receiver. And this says true, meaning keep it persistent, and keep looking at that string port, and every 10 items that come in, on every 10th item, go and call this method here, which now will be passed in a pointer to an array of strings rather than a single string. So here I go and I've created my string port at the top, then I go and activate this, then I go and add 50 strings into the port,
Okay.
and I'll just run it to completion. And here you see that it got called once with the first 10 strings, and then another time with the next 10 strings, and sometimes it was the same thread, sometimes it was a different thread. That's all, just the way it can happen.
Sure. Cool.
All right, so
That was a scatter and a gather. Just one line of code.
Nice.
all right, so now we'll start getting into some real life usages now with an asynchronous stream I/O demo. Let's say you want to do some asynchronous I/O to a stream. Now, stream, of course, is a class that's been shipping in the framework class library since version 1.0, the file stream class. What I do here is I new up a file stream to open up the boot.ini file on the root of the C drive, and I'm passing in here file options asynchronous to let the CLR and Windows know that I intend to do asynchronous I/O to this file stream. Then I have a byte array to read in at most 10,000 bytes from the file. I allocate that. Now here I create 2 ports. So the idea here is when you're doing a read operation from a stream, there's 2 possible outcomes. Either you're successful and you're told how many bytes actually got read in, or maybe an exception gets thrown because of a failure occurred. So we're going to use a port to represent each of those possibilities. The first port is a port of int32, which will get pushed into it the number of bytes that were read. And the second port is a port of type exception, because in the CLR, the way failures are reported is by having an exception be thrown. Now, I initialized both of these variables to null. Now, I needed to create, since the file stream classes and the classes shipped with the class library don't know anything about the CCR, I needed to create adapters or wrappers to integrate the existing classes to work with the architecture of the CCR. I created this class called APM to CCR adapters, which again will be, this code is downloadable with that MSDN magazine article that comes out shortly.
Okay.
And there's a static method on it, read, which will read from a stream. In fact, the first argument here is of type stream. Since file stream is derived from stream, it works just fine. The remaining arguments here, data, offset, count, those are the same parameters, identical, that you would pass to stream's read method.
Okay.
Now, the last 2 arguments, though, is the reference to the port of int32 that's going to get the result, number of bytes read, and the very last one is the reference to the port of type exception that would get the failure. Now, I'm only going to end up using one of these when the program runs, but I've created them both. Well, actually, so I null them out here, and then my wrapper internally checks to see if they are null, and if it is, it news them up. Okay, just to make things simpler for me, so I didn't have to say new here and new here. I put it in the one read, because typically you might use these ports, create these ports for every read operation. Which might seem like a lot of memory usage, but because these objects tend to live for a very short period of time, they would be in generation 0 in the garbage collector, and so they get collected pretty quickly, and so it generally is not considered to be a memory or performance hit of significance.
Excellent.
Okay, so I'm just going to step over that, and it created these 2 ports, and it issued the asynchronous read. Internally, it calls the begin read method on stream to use the CLR's asynchronous programming model internally. So now I've issued this asynchronous read. Now there's 2 possibilities. Either something will come back on the read port, which is the number of bytes read, in which case I'm going to do some processing here to process the number of bytes that were read from the file, or the bytes that were read from the file. The other possibility is that the read fails, and that's what this other receiver for is here, which gets something of type exception to let me know the failure.
Okay.
Now, because either one of these is possible, but only one, I wrap those in an arbiter choice, which says to the CLR, look, you're either going to do this one or you're going to do this one. CCR, sorry. CCR. Yeah. You're either going to do this one or you're going to do this one. Oops. All right, and then when I go and execute that, it was successful. And so it read in the bytes. We see the read completed, shows me the number of bytes, and then my code went and showed the actual bytes that were read in. That's this code right over here, this encoding ASCII get string. Got that string and displayed it in the console window.
Cool.
All right, which means this one did not execute at all. Okay, now, so that's now doing asynchronous I/O and coordinating it with the CCR. Here's another example. This does exactly what I just showed you. It is functionally identical to what I just showed you, but the syntax is a little bit different and it's easier because what I just showed you is commonly done where you use 2 ports to get a success result and to get a failure result. In this example here, I knew up the file stream exactly like I did a moment ago. I create the byte array exactly like I did a moment ago. And then I call read method, but this is a slightly different version of my read method where you pass in the same parameters, but then this version will actually go and create what's called a port set. And a port set is, exactly what it sounds like. It is a collection of other ports. This is a port set of 2 things, an int32 and an exception. Because when you do this operation, it's either going to succeed and tell you number of bytes, or it's going to fail and give you the exception that occurred.
Okay.
So my wrapper method just creates an instance of that, initializes it, and returns it back. So now I have those 2 ports created, which I did more explicitly in the previous example. Then this is another, because it is common to say I'm going to issue something and there's a success and a failure case, we have a simpler way of creating a choice, and instead of creating the arbiter.receives, you can just say, look, here's a choice on this port set, the 2 possibilities, and here's the delegate for the thing that should execute in the success case, and here's the code that should execute in the failure case.
Okay, so now the number of parameters you pass to choice, it's limited to 2? So if I had a port that had 5,
of choice, and this one is 2.
Fair enough. I just wanted to show the connection between.
Because this port set has 2.
Right. Okay. So it depends on the port you pass in.
Absolutely.
And basically it says, for each message type, give me a delegate. This is actually a generalization across threads of a try-catch. Think of it that way.
Sure.
You have general success case, you have failure case, but it's asynchronous. So give me a delegate when things go right, give me a delegate when things go wrong. In the CLR, in the APM pattern, you say begin read. Then you have 1 delegate that will get called success or failure. Then within that delegate, you have to do a try-catch around the end read operation. Here, we take that pattern that you do again and again and again, and up front, we will call that piece of code for success, that piece of code for failure. And because they're anonymous methods, he hates when I say anonymous delegates, and because they're anonymous methods, you can actually have stack, because a lot of people just love synchronous programming, because why? I declare some stack variables, and then they're available for use. Well, C# 2.0 has taken a lot of that and make it easy for us in synchronous programming. I can just mention that stack variable either in my success delegate or my failure delegate. So now you have completely concurrent programming with 99% of the convenience of the synchronous programming. And then we'll show you even more advanced stuff that even goes further in making it easier.
Very cool.
I think another benefit of this, too, is that it makes error handling, you're more conscious of it when you write your code. But a lot of times I've seen a ton of people who in the callback method, they call the end, like end read or end write, and they don't put a try-catch around it. And then in all their testing, it worked great, and then somewhere out in the field it fails. So I think with this kind of pattern, programming pattern, you're more cognizant of errors, you have to code against it, you have to consider that, and then you're going to build a more robust application.
Now, since you mentioned error handling patterns, is it ever, you usually have to catch exception when you're dealing with multiple threads, but in the general sense, it's not something you should do. If it happens to be an out-of-memory exception, or it happens to be some other sort of egregious problem, it's probably not a good idea to catch it.
Yeah,
right? So I'm just asking in terms of patterns. So in this case, because you're dealing with multiple threads, I know there is sort of...
The reason why in the CLR we say it's okay to catch exception, which normally we very strongly discourage, the reason why we say it's sometimes okay in asynchronous programming is because after you catch it, you're going to throw it somewhere else.
Cool.
You should never just catch it and swallow it whole. Right? It's because you're going to throw it, it's okay to catch it.
Absolutely. So I think we should mention that what this is doing is it's making it easier for us developers to deal with exceptions across threads, which is part of the CLR.
You can even coordinate. Think about this. You can issue an asynchronous operation, or 10 asynchronous operations. And then with a single line of code, you can say, any exception across any of those operations, first one, fire that code. And if any more get fired, your code is safe and it's going to do your error handling that really cares about the first error. It's very hard to coordinate that in the CLR. Extremely hard.
And actually, one of my demos shows exactly that scenario.
Beautiful. All right.
We're still going to get there. Okay, so now I've registered that, And now I hit enter here, and of course it succeeded the second time. It's the same exact result because it's logically it's the same exact code, just different way to pull it off.
Half lines of code.
Yep.
Okay, now here's another example. Sometimes people want to write sequential code. You want to write it sequentially, but you want to do asynchronous I/O operations. And we're starting to see programming languages now, like C# 2.0, get these features that make it pretty easy to write sequential code, even though it's executing asynchronously. And you see we've been using anonymous methods throughout this quite heavily. C# 2.0 has this other feature called iterators, which we're going to use now in order to write some sequential code, but it executes asynchronously. It doesn't block.
Interesting.
The CCR has this ability to create an arbiter from an iterator handler. And again, C# 2.0 has this method, special type of method called an iterator. It's a method that returns an IEnumerator of T. In this case, for the CCR, it's an IEnumerator of tasks that need to be performed. Then, and we give it the method a name. So this is save website to file. And what this code is going to do, well, I'll just put a breakpoint in here and we'll step over into it. So I knew what my from iterator handler, I pass in the name of the method right over here, and then I activate that on the arbiter. So we hit F10, so now some CCR thread has called into this iterator method. I now use one of my adapters to get a response from a web request. Web request is a class that's already in the framework class library and has been in there for a long time.
Yep.
I'm going to create a web request to go out to the Wintellect.com website in this example here, but of course I want to do the web request asynchronously. So underneath the covers, this adapter is actually calling the begin get response method on the web request object. And of course, a web request has two possible outcomes. It can either succeed, which would execute this delegate here where we got the data in, or it might fail, which will execute this method here, which will give it the exception, indicating the reason for failure. Now, when I initiate this request asynchronously by calling myGetResponse, which internally calls beginGetResponse, I take the result of this whole thing and I say yield return, which is a C# 2.0 construct, and really this thread then issues the asynchronous request and returns back to the CCR.
Cool.
So my thread's no longer in this method after I return. Now it's probably going out to the website and it's waiting for the data to come back. And hopefully the website is up and running. And
What website are you getting?
Wintellect.com. Uh-oh.
What do we got here? What's the problem?
Source file, would you like to bug it anyway? I think that's actually a Visual Studio thing where the PDB file and the code is kind of out of sync.
Okay.
So you couldn't hit the website.
It's not a bug in my code.
Nope, of course not.
I don't think it's a bug in the CCR either. I think it's just the builds are out of sync. So I couldn't hit it's possible I couldn't hit the website.
So there's no way to give it a
now
timeout?
Let me go and there is a way to do that, and I'll show that in another demo later too.
I bet it has to do with the proxy. We're going through a proxy controlled network here.
Well, I'm back in here.
No, it's fine. It actually, this is the beauty actually. I love this.
So here,
I love this example. What happened is we couldn't get the website, right?
No, you did. I did.
Oh, you did?
Yeah, the web data did come back.
Oh, excellent. All right.
But it just took a while.
So there was a Visual Studio problem in the debugger, which is unrelated to anything with the CCR or the demo code. But because of that, the threads were blocked. Maybe it's worth saying, but whenever you're at a breakpoint in the debugger, all the threads in the debuggy are suspended. Windows does that.
So if you were to make
It was just a debugging step by...
Yes. So we were in the debugger because Visual Studio got confused with the code and the symbols for a moment.
Okay.
It stopped the thread, so we didn't see the result. But then I set another breakpoint, said run to that. All the threads got resumed, and the data did come in and it executed.
Actually, when we're debugging the CCR, and we've debugged this up to the NT team kindly let us debug it on a 32-core machine and all that.
Nice.
The debugger gets seriously confused. Because what we do is we basically jump from thread to thread, and it's an arbitrary thread context all the time. It's really like kernel mode, but in user mode. So what happens is, just like you saw, the debugger kind of freezes. It says, I don't know where I'm at. You hit F10 one more time, but you have to hit a breakpoint, otherwise you get the entire exe dies. But he actually put a breakpoint, and now we'll continue. So
Fair enough.
It's
very cool. And we recorded that live.
There you go.
But you got the data. All right.
Yeah,
Totally.
so I got the data, and when I get the data, I set this variable web response equal to the data that came back in. So then, after I let the CCR thread return back from executing my anonymous method here, then it comes back into my iterator to do the next thing. Now, this may or may not be the same thread that executed this thing up above. We don't know that.
And it doesn't matter.
Right, and it shouldn't matter. So here I say, well, was the web response null? In which case, I said it's a null at the top, and it would not have been set here. That meant there was a failure. That meant the exception case occurred. But it's not null because I got the actual data in. So now I'm ready to take the data that I read in, and I want to save it to a file on the disk. But I want to do asynchronous I/O to the file on the disk. So I new up my file stream, and I go and get the data. And then I'm going to issue the write against the file stream to say go ahead and write this asynchronously. And there's two options that can happen. Either the write succeeds, in which case you actually get no value back at all, whereas read tells you the number of bytes it actually read. Write is successful if it wrote the number of bytes you wanted to write. Or there's a failure case here. So for something that doesn't have any value at all, we have this empty value class to say it just means that it was successful. And now when I do the yield return here, again, the thread goes back to the CCR, and now it's waiting for the write to complete, and then it'll call back into me.
Well, you're exiting now. There's nothing more to...
No, because I'm in a using directive, actually. So, because all that happened in this using statement. So it will actually call back into me. So that's another interesting thing, too. It'll call back into me because the using statement in C# has implicitly put a finally block here to dispose of the file stream. So after the I/O is finally written out, my code here will get called back into so I can close the file when it's all done.
Totally. And that's an example. I mean, not closing the file stream would be an example of a memory leak that you could write and manage code.
Right.
Well, but the garbage collector would eventually get around to, yeah.
Like in what generation? I mean,
well,
it really
whatever
depends.
generations is
As long as the application is alive.
If there's no, well,
so if it's running
the
as a
application's
service,
alive and there's no references to the object, the GC will eventually kick in and that will close the file on the disk. If the process terminates, then Windows closes everything.
Sure.
So,
Yeah.
So we're not going to leak for long.
Good. So little leaks.
Yeah.
So the interesting thing here is that traditionally, when you do asynchronous programming, you use what we call callbacks, right? And don't have a pen. Let me.
Interesting.
Let's you can continue.
Okay. Let me run to the next demo here. Okay, you want to do something on the whiteboard?
I just want to,
I
I just want to show you that because it's a pretty advanced concept that you just covered with the iterators.
Okay.
And traditionally, what we do is we say, do I/O and then call me back in callback 1, right? Asynchronously. Okay, fine. So over here you say, in callback 1, let's do the next stage of my I/O. So now do I/O 2 and call the next callback. Callback 2. And so it goes. This is what I refer to the spaghetti of asynchronous programming. You go from one to the other, and then every time, by the way, you will have to pass state and all that. Fine. In C# 2.0, maybe you can have some anonymous methods right here, and you can have the state around. But you still have this nesting. You can only kick off the async I/O for the second stage of your state machine within callback 1. So if you actually looked at the anonymous methods, the indentation goes like this. So you start in callback 1, right here, and then you have the delegate for callback 2 here, and then the indentation literally shows the literal nesting that happens because of your asynchronous. And all you want to do is a sequential set of steps. That's why people love threading. That's why they like the sequential process. Well, what we did in the CCR, which I thought was kind of a cool thing to use the iterators, you just say, okay, don't worry about it. You don't want to block any threads? Essentially, you have step 1, do I/O and yield. It will do the I/O, one of two delegates, delegate 1 or delegate 2 will get called. Now this line of code right here that I'm going to call step 2 will get called when either one of those. It's pretty cool. Even error occurred or success occurred, doesn't matter. We'll progress now here.
Okay.
Just like if I do blocking I/O. Here I would say wait for file complete.
Mhm.
Where do I continue? The line under.
In a sense, the
Very
iterator
cool.
feature of C#2 lets you write a single method, and then the compiler breaks it down into separate methods for you. In a sense, it's not really what's happening. In a sense, in a way, it really is what's happening, but but probably not the way you're thinking
Yeah.
about it.
But you took that and implemented something very
A
interesting on top
scheduler.
of
We
it.
implemented a scheduler
That can
lets
schedule
you scale.
tasks.
Right.
Yeah, in a sequential fashion, but they're happening on different threads and all asynchronously. It calls back in.
So now you have 1,000,000 24-byte tasks that could be pending, versus how many threads in 32? 2,000 NT croaks. It's a virtual memory issue. On 64-bit, you can do a lot more threads. But in terms of the cost of asynchronous items we can have, and again, you have the nice sequential programming. This is a big thing, and we use this a lot.
Cool. And yield helps out to some degree.
Well, yield does lets the compiler do the rewrite.
Got
The
it.
compiler takes
It
this.
lets you return from the middle of a method and then be able to call it back into the middle of the method right after the yield return.
like mini threading.
Very cool.
Yeah.
Coroutines.
Coroutines.
Great stuff.
Okay.
All right, we're at 45 minutes.
Oh, we got
FYI.
plenty of time.
Plenty of time.
45 minutes is plenty of time.
I mean, that's how much we.
So
that's
we
what we
used?
used. We have 15
Oh,
left.
15 minutes? Pretty close to plenty of time.
About a third less, or whatever.
All right.
About a third
So
of it.
here, a more advanced example showing more coordination and some of the clever things you can do with coordination with the CCR.
Cool.
I've created an array of image URLs. Well, URLs. And I'm going to go get something from Microsoft.com. I'm going to go get something from 1.1.1.1, which is not a valid, so that's going to be a failure. Wintellect.com and Devscovery.com, which is Wintellect's own conference. There's another plug. Now,
All right, that's 2 plugs in
I
one.
got to throw that one in. Okay, so I'm going to issue a bunch of requests to those 4 different sites. I'm going to issue all the requests simultaneously. So I have a for loop here that's going to go through each one of those URLs. I'm going to create a web request object for the first one. Then I'm going to say for the first one, let's go and asynchronously go get that response, and if it's successful, do this with it, and if it fails, then this exception will get called. Okay, and then this is in a loop. The arbiter activate is in a loop, so I'm doing it for all 4 of these requests. When any of them succeed, execute this. When any of them fail, go and execute this. And if we just let it run to the end of the method, we see some of them came back right away. Microsoft.com, Wintellect, Devscovery.com, but 1.1.1 is still outstanding because it doesn't actually exist, and eventually we're going to get a timeout, and then the exception path will kick in. And hopefully that'll be real soon now. Any second now. George, why don't you say something while we're waiting for the... Oh, there it is. Great. You don't have to say anything.
Get response fails.
It depends what timeout the system decided to use at the time.
So there we got the failure back. All right, so that's one example of coordination. Now, here's another example of coordinating. I'm going to, again, issue several requests. I want to process the responses as they come in, but when any of them fails, when the first one that fails, I want to stop all processing after that. Right, so that's kind of a difficult thing to coordinate normally. You'd have to keep track of all these requests, and when they're coming back in, there's potential race conditions that could occur. But by setting up the arbiters correctly in the CCR, it'll do all that for you, and now you won't have to think about it.
Excellent.
Here's how I accomplish it. I create a response port for the web responses that are going to come back in, and a port for the exception objects. Then I go and I issue the 4 asynchronous get responses for those 4 different URIs that I had, URLs. And when any of them complete successfully, the completion is going to go to this one response port, or if any of them fail, any failures go to this one failure port.
Okay.
First one, right?
Well, yeah, but I mean they all go in, but after the
Right.
first one, it all gets torn down. All right, so I issue those 4 requests. Oops, then I went over this a little bit too quick. But now I'm going to activate an interleave. Now, interleave is probably the most complex arbiter that the CCR supports, and it's easiest to think of it as kind of a reader-writer lock. Okay, if you're familiar with reader-writer locks for thread synchronization, it's similar to that.
And would it be fair to argue that it's the concurrency in the CCR title, interleaving. When you talk, because this is now we are talking about concurrency when you're dealing with interleave, right or wrong?
Well,
Probably wrong,
More
but,
coordination.
Still
Actually, I
The
would
way
say
of coordinating results.
yeah, it is coordination, but it's definitely used in the cases of high concurrency.
Okay.
So, coordination is always relevant. In most cases, relevant when you do concurrency. What interleave is doing, without actually grabbing a lock, it says, look, you have some things that you want to happen concurrent, no matter how many you get. If you get 1,000 messages in, process them concurrently. Great. But if you get one message in that modifies state, or maybe you want to do exclusively, what we will do is we will wait until all the concurrent items finish. We will prevent any more items from running. Run this item. When this item is done, then more things can run. All this is complex coordination people do with either reader-writer locks or with hierarchical locks, and they most definitely end into deadlocks, or with eventing or whatever. For us, it's one pattern. One group is teardown, one group is concurrent, one group is exclusive. You just put your delegate where it belongs. That's it.
Okay. Excellent.
All right, so this code here, here's what it's logically saying. This teardown group, which is the first parameter to interleave, says if any failure occurs, tear down the interleave. That means stop looking in the port for any of these items. Okay. The next one is an exclusive receiver group, which I don't have anything in the parentheses here, so no anonymous methods are being passed. So that says I don't need to do anything exclusively. Everything can be done concurrently as it comes into these ports. The last group is the concurrent receiver group. And this says that if anything comes in with a positive response, that means successful, coming in from that port, go and execute this method here. And because it's in the concurrent group, if multiple IOs come back concurrently at the same time, multiple threads can go off concurrently and process them simultaneously. That gives us concurrency.
Excellent.
Okay. Now, if I wanted, let's say that inside this method, I touched some shared state, and I needed to have exclusive access to that. So when these IOs were being processed, they had to be processed one at a time. I move this receiver into the exclusive group and out of the concurrent group, and now the CCR will ensure that only one thread at a time is executing that method.
Very cool.
That's
really cool.
We just moved the line of code. That's really cool. It is cool.
Very cool. Wow.
Okay, and then I got my hit enter over here. So they process ultimately.
You just hit enter now and it'll go, right?
Well, they should have been coming in.
They did. Thread 7. Get response.
No, this is from the previous example.
Oh, I see.
Right, so we have that get response failed.
Okay. So you press enter, nothing happens.
Oh, so one of them is going to fail, and then I tore it down. So it should have said at least one get response fail, but I don't see that.
It's the timeout again. It's gonna wait for that.
Yeah, right. It's waiting for the.
You can set it explicitly to web requests,
Correct.
so you don't have to keep waiting for these times.
Otherwise, there's a default.
All right. Well, that's not
Yeah,
worried
the
about
default
that.
timeout is ridiculous.
All right, but that will happen.
Okay. We get it. We understand. We're developers here.
In fact, it may have happened right now. Well, I'm at a break point, so this thread
All
is
right.
suspended. All right, and then here's the last one. The last one, another coordination example. Here I'm going to issue my request to those 4 URLs. I'm going to I want to process the responses after they all come in. So not as they come in, but wait for all of them to come in, or stop on the first failure. Right, so there's a different way of coordinating the results that are coming back.
Let's see.
So again, I've also have a timeout port now, because I mentioned to you earlier, I would show you how you can say, here's a timeout. So I want them all to come back in this amount of time, and I can control it this way. Or I could have set the timeout on the web request objects individually.
Cool.
But maybe you're doing a web request and a file request and something
Totally,
else.
and it
So you
makes
want
sense to
some other
encapsulate
time.
it.
And for us, time is a signal. You just issue it on a port. And the port you can coordinate, and you can join with timers, so every 10 seconds you can wake up, or all kinds of really cool stuff.
Absolutely.
With timer.
So when the CCR fires the timer, it puts something into a port, and the port is of type date time. It'll put the date and time when it fired it. So I create this port of date time over here. All right, so here I go and issue my 4 web requests asynchronously. I'll just put a breakpoint and run up to here. Then the dispatcher queue has this method on it in queueTimer that tells the CCR, go ahead and create this timer, and I want you to fire it in 2 seconds. So if I don't get a response back from the other stuff in 2 seconds, put an entry into this port. The date time will go into this port over here. Then over here, I got a choice, and I say, well, if anything failed, go and do this. Or if a timeout occurs, go ahead and execute this. Or wait for all 4 of the responses to come back, and if all 4 of the responses come back, go ahead and execute this. And again, there's potential race conditions here because all 4 of them could come back at the moment the timeout occurs, but the CCR coordinates that and ensures that only one of these methods gets called. And we do my hit enter. And there's the failure from the previous one. And now we shouldn't have to wait more than 2 seconds. Or maybe that was.
This is the one. You just fired that one.
Yeah, okay, this one just fired.
Actually, what happens because you're in the debugger,
Yeah,
the 2 seconds already passed.
that's right.
So we fired it right away.
Understood.
Yeah. And you'll show in
But the clock doesn't stop even though the threads are stopped.
Right, because this is wall clock.
Yeah.
What the CCR is using is wall clock. So even if you're stopping the debugger, it stops.
So, but if you did it as a win form where you could actually click on a button, then
Exactly.
it wouldn't matter. You just say
It's just a
do
message,
demo.
and it will say abort,
Understood.
abort. Right.
Of course.
But now it fired the timer, and you got this message saying, 1 response failed.
Great. All right. So we have 5 minutes left. This has been extraordinarily helpful, and we're going to get that URL to people.
Mm-hmm.
Let's talk about where we see this really being used. I mean, robotics, clearly, obvious, excellent example. Where else would this be cool? For like what other type of developer? When would a developer want to take this and try it in their
I
application?
mean, the clear win is anything that's I/O related, where you're coordinating I/Os that are coming in from different things. You think about mashups, for example, where you're making web service requests out to here and there and elsewhere, and then when they all come back in, then you have enough information to update the user interface or something like that. It's perfect for those kinds of scenarios.
Yeah, I mean, in my opinion, everything in some ways is about communicating, right?
Mhm.
And we knew this when I was doing driver development in NT a long time ago. Really, you send messages back and forth, but people don't want to think of it this way because programming that way is hard to keep everything in your head. And traditionally it has been the case because you have no good coordination primitives. You have wait for multiple objects, which is great. It's a join, it waits for all that. But people just always get it wrong. They didn't remember which handle and all that. Good coordination primitives make code responsive. This has never been about concurrency. Right now, your CPU is not pegged at 100%. That's why we need another core. No, that's not your problem. Your problem is that you start, your favorite Windows app, and you do some file I/O or some network I/O, and the UI is locked. Why is the UI locked? Because you were scared of all the partial failure possibilities. People cannot deal with that. So what do? They do one thing at a time, and then in a very nice way, in a very, two-way, say, failed, succeeded. Now do the next thing. Failed, succeeded. So it's never been about concurrency. Concurrency, fine. If you want to do ray tracing, if you want to do, high-end servers, yeah, that is very important. And this stuff applies just fine. But it's about responsiveness. It's about robustness. It's about failure handling. So this is applicable in all code that you care about responsiveness. And all code cares about responsiveness.
Absolutely. That's true. Now it is interesting. Please,
another feature of asynchronous programming is that the threads tend to sit idle, then they wake up, do something, come back, wake up, do something, and come back. And the way the CLR's garbage collector is architected is the shorter the thread is, the less time it takes to walk up to build up the set of roots. So garbage collections actually go quicker, and fewer objects will stay in the heap because of this model too. So it works very nicely with a garbage collected environment.
excellent. So in other words, you're saying you could increase performance when you have to have multiple threaded, let's not use the concurrency word, applications. This would be, actually, you wouldn't see a penalty. You might see any performance
Right, it would actually
improvement.
be a benefit.
Because
I just have to be careful.
Careful.
I'm being a stickler because we don't have control of the underlying memory model, and we don't know the cache coherency. We don't know the data locality. There is a penalty you pay because stuff can move around. But you know what? Very few people get that right anyway. So you might as well write robust code that has no deadlocks and get some concurrency. Maybe not 4x concurrency on a 4-proc. Maybe get 2x. That's better than wasting your CPU. So it definitely, garbage collection, I tell people, what can I use it in C++? I'm like, fine. But it's actually a very subtle problem of the ownership of the memory for that message. So garbage collection is just perfect for this type of environment. Because it's about loose coupling. I don't need to know who created that memory. It will just get freed appropriately.
fantastic.
So it has many dimensions that you could go and say why GC is good for a loosely coupled local system. When we talk about distribution, there's other concerns. But
Sure.
whatever.
Well, this has been fantastic. Thank you for the great code samples, and I'm glad to see that you got involved with this project. Clearly, good things are happening with
I've
the
had a
API.
blast with it. It's been
And
a lot of fun
you
for me.
have bought off on it. I mean, that's awesome.
It was
Mr. Windows.
It was
That's
tough.
fantastic.
But I was willing to listen to him. He had a lot of feedback, and it hurt. It hurt, but I mean, really, all we changed was the concrete syntax, the top-level syntax. The runtime, we didn't touch. You just said, no, this method, we need to make a static. We need to do this. Which I feel pretty good that we didn't have to change the underlying logic.
Sure. Well, this is great, guys. Beautiful job. And we will put the URL on the post. All right, what are we doing here? Oh. This is the cool sample you guys talked about. So what do you build using CCR?
So using the CCR, I built a tool that can capture all of the dependencies for our projects. And as you can see, we have about 90 projects. We capture the dependencies, and for each project, I subscribe to all of its dependencies, and it sends a notification back with the CCR that tells me that it's done. And the result is that I can then, as things become ready, they just start compiling. And as many CPUs as I have on my machine, I'll use them to the max. And
So look at this
let's look at
process
that.
utilization right there.
so right now, I'm still building one of my core dependencies with Physics Engine. But as soon as that's done, then the CPU will be freed up to compile as many projects as it can.
And we're at 100% right now, doing distributed MS build. This is the build system that VS 2005 uses. And we just didn't want to wait. We had 2 proc and 4 proc machines,
Yeah.
and I was using one of them.
Got
so
it.
David, in like 3 hours, basically said, calculate dependencies, shred them, scatter them, and then concurrently do the builds based on the dependency checks.
And now you can see the CPU is totally pegged.
Each one.
All 4.
All 4
Beautiful.
processors. Yeah.
And we're doing lots of file I/O. This is not like some edgy concurrency thing. This is like a heterogeneous program doing random stuff. So.
Very cool.
And it brought the build from 4 minutes and something down to
1 minute
1
and
minute 30
30
seconds.
Cool.
Almost linear scaling for the processors you have in the box.
Fantastic. Taking advantage of the multi-core.
That's
Big
right.
time. Yay. Concurrency.
Finally.
Concurrency.
Yeah, there we go.
All right. Hey, guys, we're out of time. Beautiful. Thank you for your time and great job. And appreciate it.
Thanks.